All right, our last speaker of the day is Lorenzo Vecchi, and he will tell us about Hilbert-Poincare's series of Matroid Chow rings and intersection cohomology.
Right. Thank you very much for having me here. Okay, Matroids. The plan of my talk is to tell you about some interesting polynomial invariants in Matroid theory. One interesting thing is that they arise as Hilbert series of graded vector spaces associated to Matroids. And we've already had some spoilers today and yesterday, which is great, because it means that other people are interested in it. And the reason why we're interested in these polynomials is that it turns out that they have some interesting combinatorial properties. And what I'm sharing today are parts of the results of a joint work with Luis Ferroni, Jacob Mathern, and Matthew Stevens. And I highly encourage you to check the archive version on the internet. Okay, there are very different equivalent ways of introducing matroids. I will choose to do it through poset theory. Let me give a first definition. A geometric lattice is a ranked lattice, which is both atomistic and semi-modular. Atomistic means that if you take an element, you look at all the rank 1 elements that are below it, the atoms of your poset, and you join them together, you go back to the original element. And then semi-modularity is this restriction on the possible values of the rank function. So let's look at two non-examples. The poset on the left is not atomistic, because if you take this element here, there's only one atom below, and you join only one atom, and you stay there, and you don't go back to the original element. The poset on the right is atomistic, but it's not semi-modular, because if you take this left and right atoms here, they're rank 1 elements, the join is rank 3, the meet is rank 0, and 2 is not greater than 3. Okay. For a proper example, we look at hyperplane arrangements. So you take a finite dimensional vector space over your favorite field, and you take a finite list of codimension 1 linear subspaces. How do we get a poset from this? We start intersecting the hyperplanes, and we record the possible intersections in a poset ordered with reverse inclusion. So here you have 5 planes in a 3-dimensional real vector space. The empty intersection is the whole space. Then you have your planes. Then you start intersecting planes, and you get lines. For example, the blue, yellow, and red plane give you the x-axis. It's this line over here. And if I intersect everything, I get the origin. And you can prove that the poset that you get in this way is always a geometric lattice. And the name geometric means that this poset is somehow connected to geometry, because the shape of the poset of intersection of a hyperplane arrangement looks like this. Okay. It turns out that there are much more geometric lattices than hyperplane arrangements. And in fact, there is a correspondence between the class of geometric lattices and the class of matroids. And the correspondence works like this. Matroids are these objects that abstract the notion of linear independence. So we have bases, circuits, rank functions. And from a matroid, you can build a poset. This is called the lattice of flats of the matroid. And it turns out that this lattice of flats is always a geometric lattice. So for the purposes of this talk, matroids, lattice of flats, and geometric lattices will be equivalent terms, because we can study matroids through their lattice of flats. Okay, why are we interested in studying matroids through poset? Because then we can use poset theoretic tools. For example, we can compute the characteristic polynomial of the poset. For the example that I drew before, this is the characteristic polynomial that you obtain. And you can also obtain this characteristic polynomial as a specialization of the Tate polynomial that Chris was mentioning yesterday. Why is this polynomial interesting? It's interesting in a geometric sense. If we start from an arrangement over the complex number, so a complex arrangement, we can look at what is known as the complement of the arrangement. So you start from your vector space, and you start removing all the hyperplanes in your list. What you get by a theorem by Orlik and Solomon is a smooth variety, so it makes sense to compute its cohomology. And the Betti number of the cohomology ring of this variety are exactly the coefficients of the characteristic polynomial. So in a sense, up to reparametrization, the characteristic polynomial is the Hilbert series of the cohomology of the complement of a complex arrangement. But we can compute this characteristic polynomial for every matroid, not just hyperplane arrangements. And it turns out that this polynomial has some nice combinatorial properties. The most famous one in these years is this log concavity, which was first conjectured by Heron, Rota, and Welsh. and is now a theorem by Adiprasito, Chow, and Katz. So log concavity means that the coefficient satisfies this inequality. So the square of a coefficient is greater than the one before times the one after. So in this example, 25 is greater than 8, and 64 is greater than 20. And so proof by example, log concavity holds. Okay, this is what we have. We have an Hilbert series with nice combinatorial properties. So can we find other Hilbert series associated to matroids with nice combinatorial properties? And when we started this project, we already had some examples in mind. The first one is the Chow ring of a matroid, defined by Feichtner and Judzwinski. I'm not going to stay long on this because we've already heard about it a lot. It's a polynomial ring, which you can build from the lattice of flats. So you have a variable for every element in the lattice of flats, except the bottom and the maximal element. And then you quotient out by some ideals of relations, and these are supposed to represent the relations that you get in the cohomology ring of a variety associated to the matroid. And then last year, Braden, Ha, Mather, and Proutut and Wang introduced this augmented version of the Chow ring, which is again a polynomial ring where you have some ideals of relations, and these give you the relation in the cohomology ring of a different variety associated to the matroid. But for us, it's interesting that these are graded vector spaces. Why are they interesting? Because Adiprasito, Ha, and Katz for the Chow ring, and then Braden, Ha, Mather, and Proutut and Wang independently for the Chow ring and for the augmented Chow ring proved that these two graded vector spaces satisfy the Hodge package, which is a collection of results in algebraic geometry that give you very strict constraints on how this cohomology ring should behave. And these are known as the Poincare duality, the hard-Lefschetz theorem, we've heard about it, and the last one is the Hodge-Riemann bilinear relation. I won't give you the geometric statement because we want to use them to extract combinatorial information. For example, the log concavity result by Adiprasito, Ha, and Katz can be seen as a consequence of the Hodge-Riemann bilinear relations in degree 1 of the Chow ring of the matroid. So this long-standing conjecture, which was open for decades, is now a combinatorial result, which is a consequence of a deep algebra-geometric result. So now we have graded vector spaces that are interesting geometrically and combinatorially. So let's take the Hilbert series. And we call them the Chow polynomial, H underlined, and augmented Chow polynomial, regular H. And let's see what properties they have. So Poincare duality means that complementary degree have the same dimension. This means that these polynomials are palindromic. And the hard-Lefschetz theorem, these injections and surjections we've been hearing about, tell us that these polynomials are unimodal, meaning that the coefficients go up until a certain point, and then they decrease. And here's our example, and you can see the polynomials. So these are very beautiful polynomials, and you can see both the palindromicity and unimodality. Proof by example that palindromicity and unimodality hold for every matroid. Let's see other examples. The Boolean matroid, we know what the Chow polynomial and the augmented Chow polynomials are. These are the Eulerian polynomial and the binomial Eulerian polynomial. We've heard of them a lot. One nice combinatorial property is that both these polynomials are real-rooted for every Boolean matroid. Now, if we move to uniform matroids of co-rank 1, so n elements and rank n-1, the Chow polynomial is now the derangement polynomial divided by x, and the Eulerian polynomial becomes the augmented Chow polynomial. And the derangement polynomial is also real-rooted for every n. So I hope you see where I'm going with this pattern. The conjecture is that the Chow polynomial and the augmented Chow polynomial for every matroid are always real-rooted. And this was first observed by Jun Ha, Matthew Stevens, and Luis Ferroni and Benjamin Schroeter. And the interesting thing is that we have two different polynomials in matroid theory, the Kazhdan-Lustig polynomial and the zeta polynomial. And there are also Hilbert series of different graded vector spaces associated to matroids, the so-called intersection cohomology module for the zeta polynomial, and the stock at the empty flat for the Kazhdan-Lustig polynomial. And Gideon, Proutut, and Yang, and Proutut, Xu, and Yang, when they introduced it, they conjectured that these are real-rooted. And this collection of 4 real-rootedness conjectures is what we started to call the real deal with matroids. So this is a great audience to start spreading this name. Okay, so how do we solve these real-rootedness conjectures? The issue is that we have no fast closed formulas to compute this polynomial for generic matroids. And the issue is that building the Chow ring is computationally expensive. And the only formulas that we have now is you build the Chow ring or the basis of the Chow ring, and then you extract the Hilbert series. But if we want to look at the properties of the polynomials, we don't want to do that. We want to compute these polynomials on the lattice of flats without thinking of geometry or building graded vector spaces, because that is too much. That is not necessary to study the roots of a polynomial. So here is our first formula. It's a recursive formula. If the rank of the matroid is 0, the Chow polynomial is set to be 1. And if the rank is positive, we do the following. We take every non-empty flat in the lattice of flats of the matroid, and we compute the characteristic polynomial. We divide it by x minus 1. This is also known as the reduced characteristic polynomial. And then you compute the Chow polynomial of a contraction by f. This is the poset that starts from f and goes up to the maximal element. And since the flat is not the minimal one, it's a smaller matroid, so recursively we know how to compute it. We multiply this, and we sum over all the possible non-empty flats. And the second formula is, for the augmented Chow polynomial, we again compute the Chow polynomial for every restriction, and then we shift by the rank of the flat we are contracting by. So this is great. We are doing this as invariance of the poset, and not as invariance of graded vector spaces associated to the matroid. You might recognize these formulas as the convolution product in the incidence algebra, and indeed there is a way of restating all these results as incidence algebra results. In particular, this here tells us that the Chow polynomial is the inverse with respect to the convolution product of the reduced characteristic polynomial of the matroid. But the most interesting thing for us was not that we were able to find these formulas, but the fact that I mentioned this Kazhdan-Lusztig polynomial and zeta polynomial, and if you look at the formulas that define these two polynomials, they are basically the same formula. So in a sense, we have these two Chow polynomials and these two Kazhdan-Lusztig polynomials, and the formulas that define them are basically the same formula. So now we have a way of going from the Chow setting to the Kazhdan-Lusztig setting, and this parallelism must mean something. Okay, this is a recursive formula, but maybe it will help us. Firstly, we can look at generic uniform matroids, so not just the co-rank 1 uniform matroids. And we were able, exploiting our recursive formula, to give this closed formula as shifted sums of derangement polynomials and Eulerian polynomials. And does this help us with the real-rootedness conjecture? Yes. By looking at this formula, we were able to show that the augmented Chow polynomial of every uniform matroid is always real-rooted. And the way we do it is we look at the class of matroid introduced by Haglund and Zhang, and this class of polynomials. And these polynomials are always real-rooted. And looking at this definition, we show that these polynomials always belong to that generalized class of binomial Eulerian polynomials, so they're always real-rooted. Then the formulas are indeed fast. We were able to check that every sparse paving matroid with at most 40 elements gives us always real-rooted polynomials. We are talking 40 elements, we are talking about billions and billions of matroids. So the computer really was helped by our formulas. And I'm not defining what sparse paving matroids are. I'm just going to tell you that they are a predominant class of matroids, and are conjectured to be 100% of the matroids. So whenever you find the results for sparse paving matroids, this is a huge evidence that maybe these results hold for all matroids. Okay.
When you say 100%, do you mean like as n goes to infinity?
Asymptotically, yes, thank you. So the question was, you mean asymptotically as n grows to infinity? Yes. As matroids grow to infinity, you can look at the number of all matroids, the number of sparse paving matroids, you take the proportion, and the conjecture is that this proportion approaches 100%. So of course there are no non-sparse paving matroids, but most of the matroids should be sparse paving. Thank you. Okay, but we talked about uniform matroids and these sparse paving matroids. What if I want results for every matroid? So if I have a palindromic polynomial of degree d, I can rewrite it in a different basis, this x to the I times x plus 1 to the d minus 2i. And in this way, I can use half of the coefficients. I call these new coefficients gamma. and I encode them in this new polynomial called gamma polynomial of f. And I say that f is gamma positive if the coefficients of gamma are non-negative. Why is this interesting to us? Because we have this classical result that tells us that if a polynomial has non-negative coefficients and is palindromic, this chain of implication holds. F is real-rooted implies that f is gamma positive, which in turn implies unimodality. So we have Hilbert series, non-negative coefficients, Poincare duality, palindromicity, and we have unimodality thanks to the Hard-Lefschetz theorem. Now we want to prove real-rootedness, so a nice stepping stone towards real-rootedness is showing gamma positivity, just as evidence in support of the real-rootedness conjecture. And indeed, our result is that the Chow polynomial and the augmented Chow polynomial are gamma positive for every matroid. How does the proof work? Basically, we exploit a semi-small decomposition of the Chow ring and the augmented Chow ring due to Braden, Hamad, and Pratut and Wang. So we're able to write these Chow rings as sum of smaller Chow rings and the augmented Chow rings. We extract their Hilbert series, and we compute the gamma polynomial of those Hilbert series. And then the gamma positivity is just a very nice induction. And we want to thank Botong Wang, which in a private communication helped us discussing this idea. And this result of gamma positivity, when applied to the Boolean and uniform of corank 1 matroid, gives us a self-contained independent proof of the gamma positivity of the derangement Eulerian and binomial Eulerian polynomials. We know that they are real-rooted, so they're gamma positive, but we can prove the gamma positivity independently without knowing that they're real-rooted. And then I keep mentioning this intersection cohomology module of a matroid and its Hilbert series, the zeta polynomial of a matroid. And it turns out that exploiting a different induction by Braden and Visogorets, we are also able to show that that polynomial is gamma positive. So again, we can support the real-rootedness conjecture for the zeta polynomial, even in the case of the zeta polynomial. And I think this is all I wanted to say. So thank you very much for your attention.
All right, so we have plenty of time for questions, if anyone has one.
Yeah, so I haven't encountered the characteristic polynomial of a matroid before, but so I guess one thing I am curious about is, does it, if you evaluate at a certain number, like if you evaluate at 1 or maybe at -1, does it count something?
Yes, great question. So the question is, does the characteristic polynomial evaluated at something count something? And the answer is yes. If I realize my arrangement over the, where is it? Oh, no. Over a finite field FQ, and I plug Q in the characteristic polynomial, and I look at the complement of my arrangement, the space is a finite set of points. I remove hyperplanes, which are a finite set of points, so the complement is a finite set of points. How many points? It's counted by the characteristic polynomial. And if I look at a real arrangement, when I look at the complement is just a number of chambers, so you want to count how many connected components the complement has, and if you plug -1 inside of the characteristic polynomial, you get that. If you plug 1, you always get 0. That's why we can divide by x minus 1 to get the reduced characteristic polynomial. If the matroid is graphic, the characteristic polynomial is basically the chromatic polynomial of the graph. So it counts a lot of stuff. So it's a very interesting polynomial for many different reasons, yes. Yes, it's also, the question is, I think it's evaluation of the Tate polynomial. Yes, so you can plug 1 minus q 0 inside the Tate polynomial, and you can get the characteristic polynomial. So, what, sorry?
Not the characteristic, the Hilbert polynomial.
Oh, the Hilbert series.
Yeah.
I'm not sure they are evaluation of the...
Is it a question?
Oh, it's a question, sorry. No. Oh, okay. So the question is, are the Hilbert series evaluation of the Tate polynomial? No, I think in our paper we produce two polynomials with the same Tate polynomial, two matrices with the same Tate polynomial but different Hilbert series. So the question is, since the the formulas for the Kazhdan-Lustig polynomial and the Chow polynomial look so similar, can you infer something from one to the other? I don't know. What I know is that, so I said that the Kazhdan-Lustig polynomial is the Hilbert series of the stock at the empty flat of the intersection cohomology module. In the same way, if you look at the augmented Chow ring, the Chow ring is the stock at the empty flat in the augmented Chow ring. And the intersection cohomology module is related to the augmented Chow ring, because it's a module over the Möbius algebra, blah, blah, blah. So maybe there is a way of this is exactly what we are looking for, a way of going from one way to another. Thank you. But, sorry, one last thing. The way we deduced this formula, these two formulas, was exactly, let me go back to the formulas. Okay. This formula, if you replace the Kazhdan-Lustig polynomial here, gives you exactly the zeta polynomial. And we found first this formula. And once we found that, we said, OK, there must be an analogous formula that lets you compute the Chow polynomial in terms of smaller Chow polynomials. So this is the way we infer the formulas from in this setting. Yeah. So maybe yes. Maybe my answer was yes. Thank you. Yes, so a question. Have we looked at the equivariant version of these formulas? So in the Kazhdan-Lustig setting, we are able to produce an equivariant version, meaning that instead of having a polynomial whose coefficients are integers, we have polynomials whose coefficients are representations of a group acting on the matroid. So you can look at the equivariant Kazhdan-Lustig polynomial of a matroid and the zeta polynomial of a matroid, and you basically replace the characteristic polynomial with the Ehrlich-Solomon algebra, and those formulas hold on in the Kazhdan-Lustig setting, and I believe that the same formulas hold in this setting. Instead of the Ehrlich-Solomon algebra, you look at the reduced Ehrlich-Solomon algebra, because you can divide by x plus 1 or x minus 1, depending on what the coefficients are. And then you can tensor here, and I think the same formulas hold. And actually, you can prove these formulas geometrically by decomposing the Chow ring and the augmented Chow ring in a way that looks like this. So these formulas also make sense when you look at the wonderful variety and the augmented wonderful variety. So if the automorphism group of the matroid acts on the cohomology of those varieties, so I'm 99.9% sure that the same formulas hold here. We just didn't write them down.
I guess the other thing was just, maybe I missed it, but did you say how this is proven?
OK, yes. The question.
Geometric, but there isn't always geometry, right?
Yeah. Thank you. The question is, how did we prove it? Because this looks like a geometric statement, but there's not always geometry associated to it. So the first thing we did is we have these Grobner bases for the augmented Chow ring and the Chow ring. So just by putting how many elements in each degree we have in a polynomial, this is the Hilbert series of the Chow ring and the augmented Chow ring. And this is a formula that works as a sum on the chains of flats inside the lattice of flats. And by rearranging the terms here in this formula, we were able to just group together the right thing to put together this formula. And then to show this second formula, there is a different way of defining Kazhdan-Lustig polynomials and zeta polynomials. So the Kazhdan-Lustig polynomial is the unique polynomial that makes the whole sum palindromic. And so we were able to, we took this polynomial and we showed that indeed this polynomial is the unique polynomial that makes this sum palindromic, and everything worked out. Yeah, thank you.
OK, let's. Oh, sorry, we have one last question.
Have you looked at how the polynomials you're conjecturing to have real zeros are related to F polynomials and H polynomials of simplicial complexes?
Yes, so the question is, have we looked at the connection of the H polynomial of some simplicial complex? The answer is yes. So this is another result that I didn't have time to, or maybe I did because I finished early. Early lunch. Actually, there was a conjecture by Hammerstein, Rao, and Simpson that related the Chow polynomial of uniform matroid to the H polynomial of a complex associated to the uniform matroid. So there was this conjecture, and actually rearranging the terms in this sum, we were able to show that the conjecture was true. So if that was the question, yes. So we also solved that conjecture, and the proof is ugly. It's just putting together the right thing and showing that the same formulas hold. And but it's on the paper, and I'm happy to talk about it more later.
Okay, let's thank Lorenzo again then.